Okay, in Unit 4, we're going to cover machine learning, both supervised and unsupervised machine learning, and talk a little bit about the difference between those, and then we'll look at a couple algorithms and methods for doing machine learning. So let's begin. So this corresponds to 2 units in the Stanford AI class, Unit 5, which is in supervised machine learning, and Unit 6, which is unsupervised learning. Let's take a look, and I'll highlight some of the material in Unit 5. Now there are like 50 videos in this unit. They're all relatively short, but you don't probably have time to look at them all. So I'll just point out the key ones I want you to pay attention to. First, do the intro and this introduction of machine learning. So this intro one.
Welcome to the machine learning unit. Machine learning is a fascinating area. The world
Okay, so Sebastian will walk you through introduction. He knows a lot about machine learning, so he has a really good introduction there. He's also done a lot with self-driving cars, and so 5.4 I didn't put on the list, but that's actually not a bad video also. Then we're going to jump down and skip some of this terms and get down to the spam detection algorithm and look at the spam detection question. So the idea here is that you've got
an example of machine learning is spam detection. We all get way too much email.
and so he'll walk you through talking about how this is set up and how given the words in an email message can we determine if it's a regular email or a spam email, and they call regular email ham. Okay, and so watch just the first couple of them. We're not going to go into maximum likelihood and some of this stuff, but we are going to look at Bayes classification stuff. But his overview of this is very mathematical and builds on a previous lesson where they derive a lot of the math for Bayes network and probability. And we just do not have the math background to go into this. So instead, I'm just going to have you use some of the results of this. So in our participation exercise, the first part is on this exact problem, a spam detection with Bayes network. So if you click on this link there, it'll give you a quick overview of Bayes network. And again, so we've got a set of emails that come in. These are, for our example, these are really short one-line emails. And some of them are classified as spam and some of them are already classified as ham. So this is what's called supervised learning, in that we already know what categories and we already have sample data in each of the categories. Now, there are then, we then work with a lot of probabilities. There are 3 of the 8 email messages are spam. So the probability, just if we don't know anything else, of a message coming in it being spam before we even read it is 3 out of 8. And the probability of it being ham, a good email message, is 5 out of 8. So we can calculate those just by looking at the number of messages. Then we're going to look at the words in each message, not the word order, just the words. And so we're going to take all the words in these messages and look them and count them. So click occurs, there's 9 words in the spam emails. Click occurs once, so 1 out of 9 of the messages is that. So here we do a probability, the probability of the word click being the word in an email if it's a spam, if we already know it's spam. Or like secret is in 3 of the messages. So what's the probability of secret given it's spam? So if we know a word came from a spam email, it's a third of the time it's secret here. And so we can figure out each of these probabilities because we can look through our existing mail and figure out how frequently words occur. Similarly with ham, with good email messages, we can count on those. So for example, today occurs twice in good messages, and there are 15 different words in our good ham email messages. So the probability of a word being today in a ham message is 2 out of 15. So we can figure those out. So just by looking at all of our data here, we can calculate this probability, the probability of spam or ham, without looking at any of the contents, and also the probability of a word, given that we know it's spam or ham. Now, given all that, we can use something called Bayes' formula, and we're just going to take this as is. And again, we derived this. Stanford derives this in a complicated way using math. And if you have a math background, feel free to go back to unit. I think it's unit 4 where they derive this, and then watch the videos in this. But again, it's beyond the scope, and the math is beyond the scope of this class. So we want to predict, given we have a new email message and it has the word sports in it, we want to calculate if it's spam. So this is the opposite of what we had before. We do already know, if we know it's ham or spam, and we can tell what's the chance of a word being sport because we can count how many. But we want to do the opposite. We want, given a word, we don't know if it's ham or spam. Can we predict that? So the ordering of these relations says, so this means what is the probability of it being spam given it has the word sports in it? But Bayes' formula lets us word this all, or figure this all out just using this data above: the probability of spam, the probability of ham, and the probability of sports given we know it's a spam message, and sports given it's ham message, and that information's up here. So I just want you to go in, plug these probabilities in here, and just see how we would calculate this. And again, so we're not going to go into a lot of detail on how Bayes networks works, or the theory of Bayes networks, but I just want you to see that it lets us look at data, calculate probabilities, and then use those probabilities to infer future classifications. Okay, so sorry for that jump. So that was in unit 8 through 11, and again they go through a much more mathematically inclined complex description here, which we're going to skip over. Okay, then we're going to go on. I'd like you to look at classification versus regression, which is 31 and 32 here. And I'll also walk you through this exact same example.
And my answer is there seems to be.
So he's talking about housing prices in California, where he's at. And then finally, and probably most importantly, we're going to spend some time on the nearest neighbor algorithm. And we'll be doing that as part of the participation activity and looking at in code. So go down to 50, nearest neighbor, 51 and 52, and he walks through that idea. Okay, so I'm going to talk a little bit about some of these ideas he talks about in here. First, let's talk about classification versus regression. So classification is taking some data and having some new data and predicting which of a number of discrete categories this fits into. So is this email ham or spam? We're going to look at an assignment where we look at some measurements on plants and classify this plant. Is it a tree or a bush or one type of plant or another? So that's classification. Regression is taking, again, a set of data points, and then not break them into categories, but predicting some other continuous value from those. So, for example, if we have a bunch of data here for house prices, we could predict, given a size of a house, how much it should cost. So in Berkeley, California, a house with 1,000 square feet is going to cost us, and again, so we do something called linear regression. We plot all this data and we calculate this line here that goes through, and then where does this line and again, we're not going to go to the math of how to calculate this line, but this line approximates this all this data and minimizes the distance to all of the data points. But let's say a house here with 2,500 square feet should it cost 400K 600, 800, or a million. And again, if we look at this line from the data, this is a more likely $800,000 is the likely cost for a house at 2,500 square feet. Now, just a quick point. This is Duluth, and houses in Duluth are going to cost about, so 2,500 square feet is here. It's hard to see the line. I don't have the line exactly here. But again, you're talking about $200,000 in Duluth, so a little difference than in Berkeley. Okay, and again, I'm not going to go into the math of calculating the slope and the intercept for this line, but there are certainly ways and tutorials for doing that, but it's beyond this class. Okay, next we're going to talk about classifications, not this regression where we're predicting some value from another. Now we're going to talk about, can we tell what category or class something is based on some data. So we're going to look at some different visualizations of data and how that works. So let's look at some sample data and how this classification works. So in order for supervised classification to work, we have to have a set of data that's collected that's already categorized into our categories, and we have to know what our categories are. So this is maybe some data from satellite images, for example, and we're going to try to classify points on satellite images as either water, city, forest, soil, different categories based on maybe two color readings. So here we have one color reading this direction and another color reading this direction. So we have two parameters and we're trying to classify it. And here's our known data points that are already classified. And then we've got some new data points. So we have this data point that comes in here and we want to classify that. And that's most likely some farming land, some crops. So we probably classify it here. But maybe this point is a little more complicated. What would this point or this point that's right between two things be? Is it urban or is this soil? So what were these new points? How would these be classified? So a couple ways of doing this. One is what's called the nearest neighbor classification, and we'll be doing this in our code this week. And basically from any point here, let's look at point 3, this new point, we calculate the distance to every point, every other data point, and find the nearest nearest one in this category. So that's the nearest water, and we look at that distance. This is the nearest urban, this is the nearest soil, and the nearest crop. So we calculate the closest neighbor in each of the categories, and then we just assign it to whatever is the closest neighbor. Actually, we can just look at all the distances to all the data points and figure out what's the nearest one and say it's that. We'll actually look at what's called K nearest neighbor, where we might look at the 3 or the 5 nearest neighbors and classify it that way. But this is just looking at the single nearest neighbor. And you can kind of see how this divides up the set as one option. The other thing is sometimes it takes a long time if you have thousands of data points to calculate this distance to every data point out there. So instead, we may calculate the average of each cluster of data here. And then from some new data point like number 1 here, we just would calculate the distance to the average, the mean of every data set. And so rather than having to do 1,000, if we have 1,000 data points, 1,000 calculations or comparisons, here we just have to do one comparison for each category. Now we have to do some work ahead of time to calculate all these averages, but then as we get new data points, the comparisons is faster. So that's called minimum distance to the mean, the average classification method. Another way is just box classification, parallelepiped classifications. And so we look at the range of every group, and then when we get a new thing, we try to put it in that range. There's some issues with this. Sometimes you'll have points not in a range, and sometimes you have points, ranges can overlap. So sometimes we have points in two different ranges. But that's another option. There's a more complicated statistical option. This calculates a normal distribution over all the data, each category, and then figures out the probability of a point being in each category. And this is used frequently too, and it has nice methods. But again, we're going to skip this method because of the statistics involved and look more at these two methods and look at the code for that. So here I'm going to jump to the spreadsheet data here and talk about that. Here we just had two data points. Here we're going to look at maybe more. So here we might have, maybe we have this data collected from some sort of data readings or something like that. Maybe we're reading from satellite or today often drone images. I was just at a conference 2 years ago and I met a colleague from Brazil. I hadn't known, but he was all excited. I was from Minnesota because he'd been reading lots of stuff. Minnesota's been really good at using drones and satellite images to classify forest land by tree types and do different identifications of damaged or problem trees, and they were working with the same issues down in Brazil, and so he was very excited about that. So let's say this data is from that. So what we have is we have from each image we have a bunch of features we're measuring. Maybe this is the intensity at different frequencies of light or infrared and ultraviolet and stuff. So we have all these data, and then we have some known things. And he was talking about going out in the field and actually going tree to tree and saying, oh, this tree is diseased, this tree is not, this tree is under drought, this is a different kind of tree, this is bare land or whatever, and classifying each spot on the map. So again, we have these categories. So maybe this is the reading for one data point A. That's a healthy tree. This is another healthy tree. This is another healthy tree. So we have 4 healthy trees. And now here's a disease tree and a disease tree on the map. And we have 4 disease trees. And maybe this is bare ground or something else. And this is some other category of land. Here. So for each one, we've got 10 different measurements. So rather than just an X and Y, we have 10 different measurements. So it's really hard to plot this out. Now we can plot this out in this sort of a graph here. These are all 10 features plotted out for each of the A's and B's. And if you look carefully, you kind of see a difference between the B's and the A's and the C's, the way the lines measure. And so if you have some new data point here, you might be able to say, oh, this one, see these tall blue lines, it's probably a B. But it's very hard for us to do that visually. Similarly, here we have a new data point. It's really easy with just 2 dimensions and we can just plot it out and see. But again, with real data, we're often working with 12, in this case 12 dimensions, and we're trying to figure out where this data fits. So we can do it. So if we have some new data, here's a new data point and readings. We want to decide, is this a healthy tree? Does it match like this? Is it a diseased tree? What is this spot? And so a couple ways we can do it. One is this nearest neighbor point. So we'll just calculate the distance between this vector or this set of points or measurements and this set of points. So again, we can take 28 minus 34 and see how close that is, 21 to 37, how close that is, and go through this 71 to 69. This actually looks really close to this one as we go through. And again, we can do distance. We can calculate the difference between each of these points, square them, calculate Euclidean distance in 12-dimensional space for this, which is just subtracting each of these, squaring it, and adding up all the results. So we can calculate the distance between this and A, and then this A with each one of these readings, we can get a distance to each one of these points. And then we find the nearest point here. I've actually had students do this. This is a spreadsheet. You can actually set up this spreadsheet so you can calculate the distance from this point to every one of these other points here. And what you'll find is that the nearest distance will be 1. I think it's nearest to this one, but it will be an A. So we would classify this as an A. So now we originally didn't know, but we would predict that this is an A. And same with this. We could look at this point and we'd see, well, right away we can see 78 to 25. It's probably not one of the A's. And again, when we calculate that distance here, we'll get some large distances, be very far distance from any one of these, but it looks like it's relatively close to some of these. these measurements are very close. So when we calculate this distance from this data point to one of the other ones, it's going to turn out to be a B. So again, that's nearest neighbor. We just calculate the distance to all the neighbors and work. Now, if we have thousands of tree measurements, that might take a while. So another thing we'll do is we can calculate the mean, the average, just average out all the infrared measurements and ultraviolet, all these measurements for all the A's, and have an average A and an average B and an average C. Now when we get some new data, so it takes a while to calculate that, all this averages, but now that we get some new data point, we just have to figure out its distance to the means. So we have to do these, just in this case there are 4 categories, so 4 comparisons, and find the mean that's closest. And in this case we'll look at this first point, 28. It could be a D or an A, and again we take 28 minus 30, we calculate this 21, this 29, and as we go through, we'll find eventually that this is closer to an A than to any of these other things. So calculating means takes a little more calculations up front, but then when we classify a new data point, it is a little faster because we only have to do one calculation per category, especially when you have like thousands of data points out there. So that's what this is. The other one is like this bipedal box classification. And again, that's not used that much. But what you would do is you'd say, oops, given some new data point here, 28, does it fit in here? And you look at the min and the max. So A's for this parameter go from 25 to 37, and this would fit in here. But B's don't. It go from 64 to 78, so it wouldn't fit in this box, wouldn't be in the range of values that allowed here. And same with this 21. Well, here actually we're going to run into trouble because here the range is 22 to 37, and this is just outside that range. So one of the problems with this parallelepipedal calculation is that as you can see in this picture, you do have data points that are outside the boxes sometimes. So again, we won't go into that. We're going to look at this nearest neighbor calculation in our code. So go on, you can do the participation exercise, and then we'll, in our assignment, we'll look at k-means clustering. And so let's jump back into some unsupervised learning real quick. So this is Unit 6 in Stanford.
Now I want to take a second to convince ourselves this is indeed the maximum.
Oops, let's go back here. So in Unit 6, again, Sebastian, he's an expert on machine learning. He's actually taught, there's full courses on machine learning out there, even free ones online that are really good, but we don't have time. We'll just give you an introduction to this sort of topics. So again, watch 6.1 and 6.1a, which introduce these topics, and then we want to go down to 6.4 here. Oops, wrong scroll bar. 6.4, where he talks about k-means classification, and he actually does a really good view. And actually 6.3, where he motivates this with some Google Street View stuff, isn't bad too. But let's look at this k-means clustering, and I'm just going to show you this because he does a pretty good job of explaining this.
Let me explain k-means by an example. Suppose we're given the following data points in a two-dimensional space. K-means estimates for a fixed number of k, here k equals 2, the best centers of clusters representing those data points. Those are found iteratively by the following algorithm. Step 1, guess cluster centers at random, as shown over here with the 2 stars. Step 2, assign to each cluster center, even though they're randomly chosen, the most likely corresponding data points. This is done by minimizing Euclidean distance. In particular, each cluster center represents half of the space, and the line that separates the space.
Okay, so you can watch these videos where he goes over this, and he does a really good job explaining this, but I'll just walk you through it real quickly. So again, here we're doing unsupervised learning. So we have data points, but we don't know what categories they are in. We don't have any known categories. And so we're going to do k-means clustering. Now, in all these things, k-means or k nearest neighbor, the k is always replaced by a number. So we might talk about the three nearest neighbor clustering algorithms, or in this case, the two cluster example here. So again, we're going to try to break this group into two clusters and figure out how it does. So again, we randomly pick these two clusters. He just happened to choose clusters that are relatively close to each other. And then we just divide them up. So this point is closer to this one than to this one. This point is close to here than to here, but this one is close to here than here. And so he's just drawn this visually showing that all these are in the red cluster and all these are in the green cluster. And then what we'll do, it's really neat, is we'll move this point, the center of the cluster, to the mean, the average of these points. So it'll come out here, and this one will come out here, and we'll keep repeating this, and eventually will work. Now we could do this with 3 or 4 clusters, and we'd have 3 or 4 stars here, and then figure out what works. So this is the basics. So go through this algorithm. He does a great job of explaining it, and then we will be using that in the assignment. So I'll walk you more through this when we go into the assignment and look at the code for the assignment. Okay, so that's a quick review of machine learning. I wish we could spend more time on it, but hopefully you get an idea of some of the basic concepts. And remember, towards the end of class, you're free to do some in-depth research on any of these topics.